Dear students, let us continue our learning on the course Automata Theory and Computability. We are in the second session of the module 4. In this session, we are going to cover the topics on Turing Machine, that is, the model of the Turing Machine, the representation and the language acceptability by the Turing Machine. Myself, Dr. Suresha.d from the Department of Computer Science and Engineering of Canara Engineering College, Bantwal, Mangaluru. To start with, the Turing Machine. So in the previous classes, we come across the two different classes of languages. The first one is a regular language and the next one is a context-free language. So for the regular languages, we designed finite state machines. So finite state machines, whether it is in a deterministic finite state machine or the non-deterministic finite state machines. So we come across the deterministic and the non-deterministic finite state machines for the regular languages. Along with that one, we build regular expressions for the regular languages. The next class of languages what we studied are context-free languages. For the context-free languages, we learned push-down automata and the context-free grammars which were built for the context-free languages. That is C, F, L, that is context-free languages. The next will be our decidable languages. For these classes of languages, that is the next subset. So the innermost set will be our regular languages. On the top of regular languages, we have our context-free languages. On the top of context-free languages, we have our decidable languages. For the classes of the decidable languages, we are going to learn the Turing Machine model. So the Turing Machine model is mainly built for the decidable languages. So in previous cases, in all our previous cases, what we have learned, the traversal will be done in one direction. That is, the scanning will happen from left to right. That is, the reverse is not possible. So that limitation was removed, and even that backward movement is also allowed. Such a model will be your Turing Machine model. So if we go with the architecture of the Turing Machine model, so first we used to have the input tape. Input tape will be there. Then next will be our finite control will be there. Then next will be the read-write head will be there. So these three components will make up the model of the Turing Machine. That is the input tape, read-write head and the finite control. The input tape is assumed to be of infinite length. The input tape is assumed to be of infinite length, wherein the ends are filled with the blanks. And the tape is divided into number of cells. And each cell will hold one element. Each cell will hold one element. So now to explain it briefly, there are three components are there in the Turing Machine model. The first one is a input tape, the second one is a read-write head and the finite control. The input tape is assumed to be of infinite length and the tape is divided into number of cells and each cell will hold one element. And the leaving our point of interest, the rest of the component in the tape will be blank. Leaving our point of interest, the rest of the component in the tape will be assumed to be blank. Then next will be our finite control, which is similar to that of your finite state machine, where we can have the transition description can be written. So that transitions will be given to the read-write head, wherein both the movements are allowed. That is, either we can move to the right side or we can move to the left side. And we can perform an operation on the input symbol which is there below your read-write head. I hope it is clear. That is, a finite control is now having the option of having the movement for the read-write head in both the directions. Either we can move to the left side or we can move to the right side. We along at the same time, we can perform some basic operations to the symbols which are there beneath the read write head. That's why it is called as the read write head. That is, we can write the element. So here, if you observe, the A3 is below our read write head. That is, a read write head is pointing at the A3. We can perform any operation for this A3. Like I can replace this A3 with some other symbol, let it be X. Then I can have the left movement, or I can have the right movement. So both the movements will be allowed. Left movement is maybe there, right movement may be there. I can retain that symbol as it is, or I can replace the symbol with the some other symbol. This will be the architecture of the Turing machine. So if we go with the description of the Turing machine, the Turing machine is defined by a 7 tuple. So till now we have seen 4 tuple for the grammar, 5 tuple for the quintuple, what we call it is for your finite state machine. So now it is a 7 tuple over here. So the 7 tuple will, the components of the 7 tuple will be, the first one is Q. So Q stands for states, non-empty set of states. So Q will be your states. So in case of finite state machine, we use K over there. So here we are going to use the Q, it will be used over there for representing the states. It's a non-empty set of states. Then next will be our sigma. Sigma will be our input symbols. So sigma will be our input symbols. This we have seen for if the language is binary, then the input signals may be 0 or the 1. 0 or the 1. So generally blank is not taken as a part of sigma. So blank is not taken as a part of sigma. So the end of the tape are covered with the blank spaces. Blank spaces we represent with the B. Then next is the tau. Tau is the set of tape symbols. So that is a sigma is your input symbol, but tau is the tape symbol. In the tape symbol, suppose this 0 I will replace with X. This 1 I will replace with Y. Then in the tau we will have 0 will be there, X will be there, 1 will be there, Y will be there. All such combinations will be your tape symbols. But sigma is allowed input symbol. Tape symbol we can have the replace the including your blank is also a tape symbol. Right? Then next B stands for your blank. B stands for your blank. Then first we have seen the Q for the set of states, sigma for the set of input symbols, tau for the set of tape symbols. Then the delta is your transition function. So now the transition functions will be written as, suppose I am there at the state Q naught. I have seen the symbol A. So now I can change my state, or I can retain in the same state also. I will change the state to Q1. This A I will replace with X. Then I will have the left moment. So this will be written like in this order. That is the input for the, that is now for the transition functions will have the 2 parts over there. One is the left side, other is the right side. In the left side, we used to write the first will be your state, and the second will be your symbol on the tape. Symbol on the tape. Then next on the right side, what will we write? First will be your state. That is, if we have a state change, we will indicate that one. Then next, if the symbol if we replace, A was our tape symbol earlier. A I will replace with X. That is my replacement for the symbol. Then next is the movement for the head. For the head, we have the 2 options. Either we can move towards the left side, or we can move towards the right side. That is L or the R. L indicates left movement and the R indicates the right movement over there. So that will be your delta. So delta is your transition function. Then next one is Q naught. Q naught is your initial state. Q naught is the initial state, and F. F is the set of final states. F is your set of final state, and B is your blank symbol. So these are the 7 tuple of the Turing machine. That is, in the 7 tuple of the Turing machine, if they are for the architecture of the Turing machine, you have to write the diagram which I explained in the previous slide, and you have to name these 7 tuples over there. What are the 7 tuples? The first one is Q, which symbolizes the states of the Turing machine. Sigma, input symbols. Tau, tape symbols. Delta, transition function. Q naught, start state. B, blank space F set of final states. Now, when we go for representing the Turing machine, representing the Turing machines, these are the three different ways for the representing the Turing machines. The first one is a transition diagram. Second one is instantaneous descriptions using the move relations. The next one will be the transition table. These are the three representations we use for representing the Turing machines. The first one is a transition diagram, or it is also termed as a transition graph. The second one is a instantaneous descriptions using the move relations, and the last one is the transition table. Generally, we used to write any one among them. The most preferred one will be your instantaneous descriptions using the move relations. This will be generally used. If they ask in particular, you have to write all three. Then, first, let us go with the representation by the instantaneous descriptions. For the instantaneous description representation, it is also termed as a ID over there. It is also termed as a ID. It will be symbolized in this order. If we have a string alpha, beta, gamma, let us assume a string as a alpha, beta, gamma. Fine. Where the beta is the present state of the M. That is my mission. Alpha is my left symbol, beta is my right symbol. So now the symbol under the transition, the symbol for the transition is your right symbol always, that is your gamma. So now Q0, that is beta on gamma, where will we go, that will be written. Let me take an example here. So I have on the left side I have X and the state is a Q1, and on the right side I have the B. So now I want to have the right movement. So how it will be written? So B I will replace with the assume X, then it will be written as A, B is replaced with the X, and I will change the state to Q2. Let us assume. So this is an example for your right movement. What is the transition we have written? Q1 on B, Q1 on B, the state changes to Q2, B is replaced with X, and the moment is right. So this is your instantaneous description. In place of this one, if I want to have the left movement, then it will be written as A, Q1, B. So this can be written as, if I want to have the left movement, then what happens? It will be Q2, A, and B is replaced with the X. So now this can be written as a Q1 on B, it will be, I will change the state to Q2, B I will replace with X, and the movement is left. These are the allowed movement, and this we call it as the instantaneous description. In short, we call it as the ID, or we call it as a snapshot. Fine. So this is how we write the instant representation by the instantaneous description. So you can see over here. Fine. That is Q3 is my state, A1 is my tip. So how it will be written? A2 on the left side, Q3 over here in the middle, and A1 will be written on the right side. So now corresponding to this one, we can have the left movement or the right movement is allowed over there. That is, if you can see over here, the left sequence is this one, right sequence, the symbol under read write it is A1, state is Q3. Q3 on A1, you can have the left movement or the right movement is allowed over there. Right? So this will be your instantaneous description. This will be your instantaneous description for the Turing machine. Then the next one is a representation by the transition table. The next one is a representation by the transition table. In the representation by the transition table, which is similar to the transition table, what we have written for the finite state machine. Fine. So now it will be written as first in the let me take the same old example. So what is that one? Q1 on A, I will go to the state, assume Q2, A I will replace with X, and I will have the left moment. So this will be written as a Q1 is my state, that is the present state. Input symbol is A. Fine. So Q1 is my present state. Input symbol is my A. Then this A I will replace with the X. This A I will replace with the X. And I will have the left moment, that is L. And I will change the state to Q2. I will change the state to Q2. In place of this one, suppose I want to have the right moment. I want to have the right moment. So let me write the right moment as a Q2 on 0. Q2 on 0. I want to change my state to Q3. 0 I want to replace with Y, and I want to have the right moment. To write the table entry for this one, it will be written as Q2 on 0. Q2 on 0. This 0 I will replace with Y. Then I will have the right moment, and I will change the state to Q3. This is how we represent using the transition table. I hope it is clear. So now if you go with the example which has been given over here, Q1 on blank. The blank arrow indicates start state. You know that one. It is the same convention is continued from your finite state machine. And for to represent your final state, we circle. We put a circle to the final state, so that we indicates it is a final state over there. In this case, Q1 is your start state and Q5 is your final state. Q1 is the start state and Q5 is the final state. Q1 on blank B. B I am replacing with 1. I will change the state to, I will make a moment left moment. I will change the state to Q2. In the same way, Q1 on 0. I will retain 0 as it is. I will have a right moment. I will retain the same state as Q1. Q1 on 1, no transition defined. Means I can't get 1 when I was in the state Q1. If I get that one, it's a dead state. What we have learnt in our finite state machine. We can't reach to our final state. It's in a dead state. So this is how we represent the Turing machine using the transition table. The transition table for the Turing machine. Fine. The next method. Transition diagram. Representation by the transition diagram. This is the third method of representing the Turing machines. In the first one, we represented using the instantaneous description. In the second method, we used the transition table for the representation. In the third one, we represent using the transition diagram. Right? So in the transition diagram representation, let us take the same old example. So let me take the example as a Q0 on 0. I will change the state to Q1. 0 I will replace with X, and I want to have the right moment. So this will be written as a state Q0 to state Q1. State Q0 and the state Q1. So Q0 on 0. So Q0 on 0. 0 I will replace with X, and I will have the right moment. This is how three things are written over there. The first one is input symbol. Second one is your replacing symbol. And the third one is your moment. That is your left moment, right moment. Which side you want to have the moment. That is the right moment. In this case, it is the right moment. If you take up the example which has been given over here. That is a Q1 on 0. Q1 on 0. 0 I replace with X, have the right moment. Then next Q2 on Y. I will replace with y. So means y is retained as it is, just have the right moment. Then next q2 on 1, I will replace with y and I will have the left moment. So like this, the Turing machines are represented using the diagram. These are the three ways for representing the Turing machines. One will be by the instantaneous description, and other will be by your uh, transition table and the transition diagram. Then the next one, the language acceptability by the Turing machine. The language acceptability by the Turing machine. Fine. That is, the machine will accept the M if it halts in an accepting state. If you halt in an accepting state, then we say that the machine is set to be accepted. Fine. So you can see the notation over here. That is, we have started on Q naught on W. W is my input string. I told it's an infinite length. A string is of infinite length. Then next, at some point of time, we held up in this configuration. Means no other transitions are defined over here. On the left of P, I have the alpha 1. On the right of P, I have the alpha 2. If P belongs to the accepting state, and alpha 1 and alpha 2 are the components of your tau. What is tau? Tau is the tape symbol. Tau is the tape symbol. So if it is the case, then we say that our string is accepted. Then we say that our string is accepted. If it is not the case, then we say that our string is rejected. Then we say that our string is rejected. This is how the language acceptability by the Turing machine will be decided. If we end up in an accepting state, then we say that the language is accepted, or else the language is rejected over here. It is not like that of your PDA, wherein the PDA all three conditions should be satisfied. What are the three conditions? First one is we should end up in the accepting state. Second one, stack should be empty. Third one, input should be empty. All three conditions, if they are satisfied, only then we say that the string is accepted in the Turing machine, in the PDA. What is PDA? Push down automata. But in case of Turing machine, it is not the case. In case of Turing machine, if we end up in a scenario wherein on the left of the state we have the alpha 1 and in the right we have the alpha 2, and that state is an accepting state, and no other transitions are defined for the alpha 2. In that case, we say that the language is accepted. Fine. So now let us take one simple example over here. Let the string is 0, 1, 1. This is the transition table which has been given. Fine. So first, I started with the state Q1. First, Q1 on 0. What is that one? Q1 on 0 is x or x2. So 0 is replaced with x. I will have the right moment, that is next here it will come Q2. Then left out is 1, 1. Next, what is that one? Q2 on 1. Q2 on 1. What is that one? 1 is replaced with y. Moment is left. Change the state to Q3. So now the moment is left. It should come here. That is here. That is Q3. 1 is replaced with y. 1 is replaced with y. This x as it is. Again, Q3 on x. Q3 on x. What is that one? X or Q5. X as it is. We have to have the right moment. So it will come over here. Then next is your Q5. Then Q5 on y. Q5 on y. So y it will be y r and the Q5. That is I will have the right moment over there. Then Q5 on 1. Q5 on 1 is not decided. So Q5 on 1 we don't have anything over here. So when we don't have anything over there, the machine will stop. When the machine will stop, does Q5 is an accepting state? No. Then it is rejected. Then it is rejected over there. Fine. So this is how we decide. This is how we decide whether the machine ways your input is accepted or rejected. Input is accepted or rejected. In the second example, if we have the input as 0, 0, 1, 1, 0, 0, 1, 1. First, Q1 on 0, x, right Q2. 0 is replaced with the x, we will have the right moment as Q2. Then Q2 on 0, 0, right Q2, 0 as it is, then I will have the right moment. Then Q2 on 1 is I will replace with the 1, I will replace the y and the left moment. left movement. Q3 on 0, 0 L Q4. Then 0 as it is, I will go to the Q4. Then Q4 on X. Q4 on X, it is a X right Q1. It is I will make the right movement Q1. Again Q1 on 0, I will move back. I will move front. Then Q2 on 1, I will change it to Y and I will come back. Fine. Then next. So in the last scenario, so what we will get a blank and the Q6. So next to the we are ending up at the Q6. When we end up at the Q6, no other transitions are defined. Then next check Q6. What Q6 is? Q6 is accepting state. So your string is accepted. So your string is accepted. Fine. That is when we end, which is not matching any of the transitions. If we end up in an accepting state, then we say that our string is accepted or else our string is rejected. This is how the acceptance is decided in the case of Turing machines. The references for this presentation are taken from the textbook KLP Mishra, N. Chandrasekharan, 3rd edition, Theory of Computer Science, PHI 2012. Thank you.